All right. Well, happy Monday and happy 10th week. Oh, what? My password's wrong. Okay. So yes, on Friday we've got an exam. It's technically our final exam, but it's only 45 minutes long. Okay, it's only worth 15% of your grade. So I don't want you guys to feel extreme anxiety about this thing. Okay, and this is what I've decided to do today. And I'm just kind of like revising what I'm working on. But basically today I will post a document with about, I don't know, 10, 15 questions on it, okay? And these will be the questions that will appear on the final exam, okay? So I'm giving you all the questions straight up. And then the final exam, I will just pick, I don't know, a handful of those questions out of that pool, all right? And all of the questions, don't laugh, all right? All the questions are mostly conceptual in nature. There might be like one or two questions that are calculation based, okay? But most of them are conceptual in nature. Most of them are, I don't know about most. Well, okay, some of them are like big picture stuff from the like, you know, like what's the point of Monte Carlo methods? That's like one of the questions, okay? And you would tell me, okay, you're breaking my heart here, but what's that?
So we don't do hard math.
So we don't have to do hard math, right? And we've got probability questions, questions related to you know some kind of question that can probably be boiled down to a something based on a probability distribution, and maybe we can't do the hard math, right? Okay, and Monte Carlo methods. I guess another question's like, you know, why do we generate a random sample? Like, how is this going to help us? I forget the exact wording. It's a little bit better when I have it written down on the document. Okay. Other questions will be related to the Metropolis algorithm and Gibbs sampler. And they're mostly conceptual in nature. So again, the document with all of the questions that will appear on the final exam, I will post later today. And that's that. You guys probably making it too easy for you, but I guess that's okay. You guys are allowed to like talk to each other as you study to like come up with a general consensus that this is the correct answer, and then on the final, if you studied, then you'll be fine, right? So, but you know, and if you didn't study, if you didn't, then you'll probably be in trouble. But I hope that relieves some uncertainty and undue stress regarding the final exam. Okay. Are there any questions about that? Yes. Oh yeah, we'll do attendance. So I guess. All right. So we'll do attendance. We'll say today will be our last attendance. Okay. That means no one's gonna show up on Wednesday. But I don't want to say no one, but we'll. All right. Come to class on Wednesday. All right. Don't. The reason why you come to class shouldn't just be like this one little half a quarter of a point or whatever it is, but okay. Letter A. All right. It doesn't matter. So we'll do that. Okay. Attendance. Yeah. I guess I'll go through and I'll try to get your attendance grade updated. Yeah. Okay, and then the last homework 6. Yeah, I'm working on that. I'll try to get that up. If not today, tomorrow, or I guess at the latest Wednesday, and I'll give you guys a week to get it submitted. It'll be so today we're gonna take a look at a document that I think is a good application of the Gibbs sampler. Okay, so when we teach, I'm always using these just toy examples, just showing like the very basic bare bones parts of how the algorithm works. But when you do that, you don't realize how powerful some of these methods are. So we'll look at a decent application of the Gibbs sampler, and I think that will be good. Okay. Oh, whoops. That's okay. Course evaluations are open. I hope you've enjoyed the course, and please leave me your reviews. I do read them after all the grades have been filed. Then they release the course evaluations for me to read, and I take all your comments to heart. And that's that. If you really like the class, I encourage you to leave a review at like Bruin Walk or someplace like that. And anyway, okay. Any questions before I get started with the content? A. Okay. But it doesn't really matter. I'll just check to see if you answered the question today. Okay, so look for that document with kind of the final exam questions. Oh, and this is important. Don't share that document with people outside the class. Okay, so it's just for you guys. I'm trying to be nice. Please. There's a mutual thing going on here, right? I'll be nice to you. You just be respectful of my wishes. So. Okay, so that final exam questions will be posted later today. You guys can take a look at that, study, and all right. So there, I posted a document on CCLE under week 10, or a link to it. It's called Gibbs Sampling for the Uninitiated. The first half is all about Gibbs sampling and how the Gibbs sampler works, or at least until page 7, and then we will look at. Starting in, I guess, section 2 of the document, it says, deriving a Gibbs sampler for a naive Bayes model. Okay, so what we're going to do is we're going to use the Gibbs sampler for document classification, okay? And originally, so the application that this article covers is for sentiment analysis, but really it could be any kind of document classification. So one use is sentiment analysis, okay? And sentiment analysis, this used to be a huge thing, and it still kind of is. It's still a big deal, but you go back 7 years ago, this was a really, really hot topic. I think it's still pretty important. Facebook I don't know how long ago. It used to just be you could only like statuses, and now you can like and love and haha them and whatever, sad face. You can't do a thumbs down, but I guess that's what Reddit's for. So anyway, that was not just to, well, I mean, I guess Facebook wanted to improve the user experience, but they're also analyzing all of that as part of sentiment analysis. Basically, when you click love versus haha versus angry face or sad, you are giving data to Facebook that they can then use. You know, you're basically labeling the data for them, and then they can run all of their learning algorithms to try to understand the human mind and language and stuff. Okay, but anyway, sentiment analysis, if you're not familiar, basically takes something that somebody said, and the computer, using some kind of data model, is trying to say, this person feels like positive or negative about whatever they're saying, right? So, you know, you say, you see a tweet that says like, OMG, I don't know, whatever, this is so great. That's going to be a positive thing, right? And then somebody else says, you know, this is trash, this is such a stupid, or, you know, that will be a negative sentiment, right? So sentiment analysis, you know, is, you know, statement is positive, versus statement is negative. Okay. And that's basically all we're doing, okay? In this case, a document is a 140 character tweet. Oh wait, it's 280 now? I don't know, whatever they did, okay? So the document is just, is something, a set of words, okay? And then the classification is positive or negative, okay? But this could be further extended. So in sentiment analysis, or at least in this example that we're looking at today, there's only two classifications, positive and negative, you know, 0 or 1, whatever it is, okay? But this can be extended to say like, oh, this is a news article about politics. This is a news article about natural disasters. This is a news article about, I don't know, economics and crime or whatever. You know, these methods at its heart can be extended to more complex systems, okay? We're going to take a basic approach, which is kind of known as the bag of words approach, which we just say like, what are the words that appeared in this document? And based on the words that appear, we're going to try to figure out the sentiment, okay? So if we see words like super, awesome, and great, and cool, and I don't know, whatever, then that would probably mean the person is feeling positive about the thing that they're speaking about, versus, you know, if we see words like bad and awful and terrible and things like that, then it would most likely be negative, okay? The bag of words approach, when we're just looking at one word at a time, doesn't pick up little nuances, right? If someone says, yeah, right, that usually means they don't agree with the statement, okay? Bag of words is not going to pick up on that, right? So somebody says like, so-and-so is the greatest president of all time, yeah, right. The bag of words will just think that's a very highly positive thing, but we know that's not what this statement is saying, okay? So, you know, I mean, there's significant shortcomings, but we're making a simple model, okay? All right, and so this is going to be how our model of how a document is generated, okay? okay? And we're gonna say there is going to be a label, okay? So we're gonna say we have some document J, right? So you've got, I don't know, 100 documents, okay? You got document 1, document 99, document 50, okay? We've got some document J, and document J has label LJ, okay? So LJ can be 0 or 1. And this will be either indicating which class of document is it. Is it a positive document? Is it a negative document? Is it a document about, so that's if you're doing sentiment analysis, positive or negative documents. Maybe you're going to do an analysis on is the document about cars or not, okay? I don't know, maybe something, right? Okay, so LJ can be 0 or 1, and it's either, it's either in the class or it's not. So this is the class of the document. Okay, and associated with label 0 or label 1 is going to be a vector over, I guess, our word space here, okay? So, well, here, okay. So document J has label LJ, and we will say L sub J is going to be drawn from a Bernoulli with parameter pi, okay? So some document J has label LJ, and LJ is drawn from a Bernoulli distribution with parameter pi, right? So pi will be the probability that the document has LJ equal to 1. Week 10, Monday. Okay, and then and there is so class 0 has a probability vector theta 0 associated with it. Okay, and so does class 1, okay? And class 1 has vector theta 1 associated with it. Okay, so theta 0 and theta 1, these are vectors of probabilities over all the words, okay? So theta is a vector of probabilities over all the words, or maybe, I don't know. So technically theta would be a vector that's like, I don't know, 80,000, of length 80,000. That's assuming there's 80,000 words. I don't know. Let's keep it simple. Let's say there's 50,000 words that we'll put in our model here, okay? Maybe even less, all right? So theta is going to be a vector over all of these words. And let's say 0 will be positive, okay? Then theta 0 will be, I don't know even how to draw this, but words like bad will probably have, small number, where good will have a high value, and awesome, it will be high. Okay, I don't even know what order, what magnitude these words are, because there's 50,000 of them, and awful would have a small value, and then a bunch of other words would probably just have neutral values. Okay, so
it's like the decipher.
No. Oh, okay, kind of like the lexicon, right? So, but for the deciphering lexicon, it was just, what's the probability that this word appears? Okay, and this would be, I guess, a tweaking of that, where you take all the positive words and you increase their probabilities, and then you take the negative words and you decrease their probabilities, so that the sum of all the probabilities still adds up to 1, right? So you say, for all, 50,000 words or whatever, okay? Okay, and then theta 1 for negative, this would be, bad would have a high value, and then good would probably have a lower value, et cetera, et cetera, et cetera, for all 50,000 words, okay? And, if you sum all the thetas, theta 0 sub I, from I equals 1 to 50,000, that would add up to 1, okay? So you have a probability associated with every single word. All right, is that okay? Yes, question?
Words that have a positive or negative.
No, I mean, I guess it depends, right? It doesn't matter, really, okay? Because if the word house has the exact same value in vector theta 0 as it does in vector theta 1, then it's not going to make a difference in terms of the role that, because what we're going to do is, based on the words, we want to create a probabilistic association and say, like, okay, I saw the word good and I saw the word house in my tweet, and I want to decide, is this a positive tweet or a negative tweet, okay? The word good has a high value in the positive vector, and it has a low value in the negative vector, okay? The word house has a medium value in the positive vector and a medium value in the negative vector. They actually have the same value in both. And so the word house is not going to really play a factor into determining whether it's going to be categorized as positive or negative, whereas the word good will, okay? So yeah, you could do all 50,000, or you could just say, we're only going to look at these words that are associated with positive things and these words that are associated with negative things. That's also fine, okay? If it's the exact same value in both vectors, then yeah, you can throw them away, okay? And in the homework, to kind of keep things simple so you don't have to have these vectors of 50,000 words, okay? Because we're going to do an unsupervised learning, so I'm not even going to tell you, like, these words are positive words and these words are negative words. You're just going to look at the corpus of documents and figure out for your, like, the system will try to figure out for itself which words are positive and which words are negative. To kind of keep it simple, we're going to look at two children's books, okay? One is going to be Green Eggs and Ham, okay? Because it's by Dr. Seuss. Green Eggs and Ham is known. Do you guys know the story about, like, how Green Eggs and Ham was written? It was like somebody created a challenge for Dr. Seuss, and it was basically, can you write a complete book with 50 words or less type of thing, okay? And Green Eggs and Ham, I think, has only 50 unique words in the entire thing, because it's just like, I will not eat them in a box. I don't know, whatever. I will not eat them with a fox. And this way you'll have at least a manageable thing. And then the other one is Go Dog Go, and Go Dog Go is another kid's book, and it's just about, like, big dogs and little dogs and black and white dogs, and I don't know what else it says, but I was probably influenced by the fact that I had to read these books to my daughter, and I'm like, oh yeah, this will make easy document classification things. Okay, so basically, I just took the text of those books and I just chopped them up, and as a human, it's really easy for you. Like if you see like 2 words taken out of the document, will basically be like 2 lines from the book, and I would say like, did this line come from the dog book or did this line come from the Green Eggs and Ham book? And I'm pretty sure you guys would figure it out easily, right? Because you are people and have read books, okay? But can we also just give completely unlabeled information to the computer and not tell it that these books came from, that these lines came from the dog book and these lines came from the Green Eggs and Ham book? Can the computer also sort these out themselves by looking at, word similarity and things, okay? Well, anyway, sorry, I'm getting ahead of myself. Right now, we're just looking at the vector over all of the words, okay? And so, we have this vector, and then, so for document, if document J has label L sub j equal to 0, then it uses the vector theta 0, okay? And the words that appear in document J are determined. So this is like a vector of all the words. This is determined by the multinomial distribution with R sub j. This is the number of words in document J, and theta, technically L sub j, okay? Which in this case is theta 0. Right? So document J has label 0 or whatever, okay? And document J has, let's say, 50 words in it. The count of the words that appear is going to be drawn from the multinomial distribution, okay? And again, we're treating this as a bag of words where the order of the words themselves are not really factored into our understanding of it. We're just looking at word counts. The word good appears 3 times, and the word house appears 1 time, and the word, I don't know, whatever, okay? Based on seeing the word good appear 3 times, we're going to classify this as a positive sentiment thing, okay? Or something like that, right? You guys are familiar with the multinomial distribution? Okay, it's like, so in the binomial distribution, it's how many times did you get heads, and implicitly how many times do you get tails, right? Because the number of heads and tails have to add up to n. And in that case, it's just yes or no, heads or tails. Okay. Multinomial would be something for a categorical thing, right? Like if you roll a dice or roll a die, and there's 6 sides, and each side is equally, has certain probabilities associated with it. You can say, if you roll the die 100 times, how many times you see the face 1 versus the face 2 versus the face 3, those will be determined by the multinomial distribution, okay? So it's like the binomial, except instead of having only 2 outcomes, yes or no, multinomial allows for n number, or k, or whatever letter they use, number of outcomes, okay? You have more than that, okay? So the words that appear in document J are determined by the multinomial distribution. All right, is this okay? We want to set up some prior distributions, okay? So, so keep in mind, so we said L sub j, Lj being the label, this is drawn from the Bernoulli with parameter pi, okay? So pi itself would be drawn from, what's the conjugate prior for the Bernoulli or binomial? A beta distribution, right? So here we would have a beta distribution, and we will give it, just to follow the notation that's in the document, because I do want you guys to read the document, okay? We'll give, we'll use the prior parameter gamma sub pi, okay? So, so the labels come from Bernoulli, okay? And then pi comes from a beta, right? And beta is basically 0 to 1, and you've got something like that, or maybe, okay. Gamma sub pi, this is technically a vector, okay? Because beta has, the beta distribution is determined by two values, right? An alpha and beta shape parameters. So gamma sub pi, this is a vector that contains alpha and beta, okay? The shape parameters for the beta distribution. So I don't know, maybe I'll put an arrow over that to indicate that it's a vector. Okay? All right, meanwhile, the words, so this is technically the word counts. Word counts in document J come from a multinomial distribution with parameters Rj and theta sub Lj, okay? Theta being, the vector, the word probability vector associated with label Lj, Lj being 0 or 1, okay? And I don't know if you guys know this, okay? So the beta distribution is the conjugate prior for the Bernoulli and binomial distributions. The conjugate prior for the multinomial distribution is the Dirichlet distribution, okay? And here we'll use gamma theta, okay? And again, this is a vector of many values. To decide the Dirichlet distribution. Okay, so so the beta distribution looks like this. It goes from 0 to 1. The Dirichlet distribution looks like a multi-dimensional version of this. Okay, so the Dirichlet is like a multi-dimensional beta. So like if you were going to draw a Dirichlet distribution for the sides of a cube, okay, you would have like from 0 to 1, this would be like the distribution for, side 1 or word 1 and, 0, 1. Okay. Side 2, side 3, etc., etc. So that basically, because the multinomial distribution has this parameter theta, which will be like the probability of side 1 is this, and the probability of side 2 is, 1/6, and the probability. But if those were not predetermined, what's the probability of getting each side? Those values will be coming from the Dirichlet distribution, okay? And if you got 6 sides, then 5 of those values would be drawn from here, and then the last one would be whatever is needed, so it adds up to 1. Okay, so the Dirichlet is a kind of a multi-dimensional version of the beta distribution. Is that okay? All right. Oh man, I'm taking too long. Okay, let me draw the plate diagram. Okay, so here we have gamma pi. This is the prior on pi. From here, we draw our value pi, the probability that a document will have some label. And then this from pi, for each document, okay, so there's n total documents. For each document, we will draw a value Lj. Okay. Over here, we've got a prior. This is kind of the prior on the labels. And this is the prior on the words. Okay. This is going to determine the here there's 2. Okay, there's a theta 0 for class 0 and a theta 1 for class 1. Okay. So there's, a vector of probabilities of all the words for positive documents and for negative documents. Okay. And together, based on the Lj, we are going to determine kind of the word counts of each word that appears in the document. Okay, and there's RJ words in document in the document. Okay. Words in document J. Okay. So the data that we have is basically a count of how many of the words that appeared in the document. The word good appeared 3 times. The word yes appeared once, and the word house appeared once, and the word cool appeared once. Okay, this is the document, and based on that, we want to figure out what's the associated label. Okay. All right. So there's a few more letters that are going to appear. Okay. In our kind of our joint distribution. Okay, so I've got this. This is kind of the corpus. This is the set of all documents. Okay, and then we've got C0. This is documents labeled 0. Okay. And then we're also going to have all documents except document J. So if you, so the corpus C would be all the documents, okay? And then you might have C0 slash C1. So this would be the documents labeled 1. And then you'll also have the documents, because when we classify whether document J is positive or negative, it's going to be based on all of the other documents. Okay, and so this is what we have. Okay, and so we have the entire joint distribution. Let me just see if there's other. Okay. All right, I'm going to go on here. So the joint distribution of everything is going to be the probability of our entire corpus, all of the labels, okay? The probability of the label, pi, the vector of words, word probabilities theta 0, the vector of word probabilities theta 1, given, so when you have the semicolon, it's given generally parameter values, okay? When you have the vertical bar, it's given, I don't know, some variable condition, okay? But anyway, given the parameters, the hyperparameters in this case, gamma pi, okay, and gamma theta. Okay, so given these are kind of our hyperparameters. Okay, and again, gamma pi consists of 2, so we could further split that into gamma pi 0 and gamma pi 1, or okay, and we will decompose it. Oh man, decompose 2. All right, so we're gonna say, all right, first we need to figure out the probability pi, and this is determined by our gamma pi vector, right? Gamma pi 1 and gamma pi 0. So this is a beta distribution. Beta distribution to determine the value of pi, because pi is the probability of the label, okay? And then once you have pi, then you figure out, then you draw the labels given pi, okay? So this will be Bernoulli to determine labels L. Okay. We also have to figure out the word vector, theta 1, given our gamma thetas, okay? Or actually, we got both of these. We got probability of theta 0 and probability of theta 1 determined by gamma theta, okay? So these are Dirichlet distributions to determine the vector of word probabilities. Okay. And then once we have our vector of word probabilities, we've got to figure out kind of the entire corpus of documents. So we've got corpus of documents labeled 0, and those are determined by theta 0, and the L's that are labeled 0, okay? So this is, the corpus will be kind of all the words in all the documents. So this is basically the sum of the multinomial vectors. Determined by theta 0 and the labels. Okay, and then I'm running out of space, but basically the same thing, but this time you've got the corpus for documents labeled 1 determined by the multinomial vector for theta 1. Okay? And this is going to be the joint distribution for everybody. Okay, well, I guess I run out of time. On Wednesday, we'll talk about running the Gibbs sampler to get this and then figure out the labels, okay? But I think it's pretty cool. All right, so I'll see you guys on Wednesday. I'll post up those documents and the homeworks, and so take a look at that, and we'll see you guys on Wednesday.